Welcome back to the Deep Dive. Today we're getting into the real nuts and bolts of model engineering with DeepSeek v3.2 XP. And this isn't just, another model with a few more parameters. It's a big, dedicated experiment trying to solve maybe the single biggest problem in scaling LLMs, that quadratic cost of attention.
Exactly. We're looking at a model that's a direct continuation of DeepSeek v3.1 Terminus. But the mission here was incredibly focused. How do you get way more efficient without losing that top-tier performance v3.1 was known for, especially when you start pushing context lengths out to something like 128K tokens?
And that brings us to the core idea, this thing they call DeepSeek Sparse Attention, or DSA.
Right. For anyone working in this field, that O of L squared complexity, it's just the final boss. It's always the bottleneck. DSA is their custom-built answer to that. It's engineered for one thing, really. Huge efficiency gains in both training and inference, specifically in those long context situations where the normal cost just becomes, well, totally prohibitive.
Okay, so that's our mission for this deep dive. We're going to unpack how they pulled off this balancing act. First, we'll break down the architecture change, DSA itself. Then, the really interesting part, the two-stage training they had to invent to make it work. And finally, we'll dig into the results, which claim they've reached performance parity and in some places even gains over the original dense model. Can you really go sparse and not pay a price? That's what we're here to find out.
When you look at the design, the most striking thing is how minimal the change really is. Architecturally, DeepSeek v3.2-X Terminus, the only difference is that they've layered DSA on top through this very specialized continued training. They didn't have to rip out the engine and start over.
It's more like a surgical upgrade. And this DSA system has two main parts working together. First, you've got this component they call the lightning indexer. Think of it like a relevance radar. It's figuring out which tokens from the past are actually important for the current token.
And then second, you have the fine-grained token selection mechanism, which takes the output from that radar and actually does the sparse math. Let's focus on that indexer for a second, because that's really where the magic starts. For any given query token, let's say H sub t, the indexer calculates a score for its relevance to every single token that came before it.
And the computation itself is designed to be incredibly cheap.
Incredibly cheap. It's a summation across just a handful of indexer heads using these derived vectors, Q sub t and K subs, from the input. And what's really fascinating from a technical standpoint is the choice of the ReLU activation function. They state explicitly that this wasn't for modeling power, but purely for throughput consideration on the hardware. It's just faster.
That's a pure engineering decision right there.
Absolutely. And they add to that by using a small number of heads and implementing the whole thing in FP8 precision. All of this ensures that even though it's technically an O of L squared calculation, the actual computational cost is, almost negligible compared to the main attention block.
Yeah. So you have this super fast, low-cost O of L squared guide that runs first. And once it generates those scores, the fine-grained token selection mechanism kicks in. This is where the model actually becomes sparse. It only grabs the key value entries, the actual information, for the tokens that got the top K highest scores from the indexer. And K here is much, much smaller than the full sequence length, L.
Right. So the final attention output, the thing the model actually uses, is computed using only this plenty filtered subset of key value pairs. It's a way to force the expensive part of the calculation to focus only on what the cheap indexer already decided was most relevant.
Okay, but how does this new DSA module actually fit into the existing architecture? The baseline model uses something called multi-latent attention, MLA. So they had to make it compatible.
They did. And that compatibility was paramount. The DSA was specifically instantiated based on the existing MLA framework so they could continue training directly from that v3.1 terminus checkpoint without any major disruptions.
And within MLA, there are different modes, right? MHA and MQA.
Yes. And they chose to build DSA based on the NQA, or multi-query attention mode. This decision was basically forced by the raw efficiency needs at the kernel level. For this whole sparse system to actually be faster, the design required that each key value entry that gets selected has to be shared across multiple queries.
To maximize memory efficiency, makes sense.
Precisely. In the MQA setup, every latent vector, which is the key value entry, is shared across all the query heads for a given token. That sharing creates a massive memory saving, which is non-negotiable when you're dealing with a 128K context. It's how they ensure that when they fetch those top EI tokens, it's done as efficiently as humanly possible.
And it's worth remembering that the V3.1 baseline already used both modes. It used multi-head attention, MHA, for training and pre-filling, but then it would switch to the more efficient MQA for decoding.
Exactly. So by building DSA on top of that MQA framework for the continued training, they basically ensured the new sparse mechanism inherited all the memory optimizations needed for it to work at scale from day one.
We've covered the what, but the how is just as critical. How do you actually train a giant model to trust this new, sparse way of seeing the world?
Right, that's the multi-billion token question. The foundation was that pre-existing DeepSeek v3.1 terminus checkpoint, the one already trained on a 128K context. And they were careful to align the data distribution for this new training phase with what was used for the original long context extension.
And it's not one single training run. They broke it into two very different, very critical stages. The first one is called the dense warm-up. The goal here is simple. Just initialize the lightning indexer, get it working correctly before you turn on the full sparse system.
It's like building up the indexer's muscle memory. And during this phase, they actually keep the full, dense attention mechanism running, and they freeze all the other model parameters. The only part of the entire model that is learning anything is the lightning indexer.
And how is it learning? What's the loss function?
It's a KL divergence loss. Essentially, they're measuring how different the indexer's predictions of what's important are from the actual dense model's attention scores. They're using the full, expensive model as a teacher. The indexer is just trying to mimic the attention patterns of its dense parent.
That's a really clever form of distillation just for this one component.
It is. And this warm-up phase is pretty short, only about 1,000 steps, which is around 2.1 billion tokens. It's a quick, focused stage just to get the indexer ready.
So it can reliably spot the important tokens before they flip the switch and introduce all the instability that comes with actual sparsity.
And then comes phase 2, the STARS training stage. This is where the real adaptation begins. Now they activate the fine-grained token selection and the objective changes. They unfreeze everything and start optimizing all the model parameters to adapt to this new sparse attention pattern.
The alignment with the indexer continues, I assume.
It does, but now, because the model is only seeing the selected tokens, the KL divergence loss is only calculated over that selected set, which they call S sub t.
Okay, that makes sense.
But here is the most brilliant and I think most critical part of the whole training process. For stability, the indexer's input is explicitly detached from the main computational graph.
Wait, detached. If they wall it off like that, where does its training signal come from? If it's not getting feedback from the final language modeling loss, whether the model's final answer was right or wrong, how does it improve?
That's the key to making it stable. The indexer's training signal comes only from that KL divergence loss. It's only ever trying to get better at mimicking the dense teacher. Meanwhile, the main model, the rest of the transformer, is optimized only using the standard language modeling loss. This separation prevents the indexer from being jerked around by the noisy, chaotic gradients that can come from the final prediction task, which could easily mess up the delicate selection mechanism.
That structural firewall is probably the only reason this works. It's an incredibly aggressive change. And the scale of this stage is just huge. 15,000 steps, nearly 1 trillion tokens. And they're selecting 2048 tokens for every query. It really shows you how much training is needed to bake this new behavior into the model.
So after all that pre-training, they made a really important decision for the evaluation. They kept the post-training pipeline, the algorithms, the data, everything exactly the same as it was for v3.1 terminus.
Which is smart. It means any performance difference you see at the end can be confidently attributed just to DSA, not to some other tweak in the fine-tuning process.
A big part of that pipeline is something they call specialist distillation. They take the base v3.2 checkpoint and then use large-scale reinforcement learning to create specialized versions. One for math, one for competitive programming, one for agentic coding, and so on.
And those specialists then become data generators.
That's right. They generate high-quality, domain-specific data, including examples of both long chain-of-thought reasoning, the thinking mode, and just direct answers, the non-thinking mode.
And the process works really well. The models they train on just this distilled data end up performing almost as well as the original specialists, which really confirms the whole knowledge transfer concept.
And then the final step is what they call mixed RL training. They use an algorithm called Group Relative Policy Optimization, or GRPO. And the big innovation here, if you look at how DeepSeek has evolved, is that they've merged everything, reasoning, agent skills, and human alignment into a single RL stage.
That's a huge shift from their older models, which used multiple stages. The idea, I guess, is to balance performance across all those different skills at once and hopefully avoid the model forgetting one skill while it's learning another, that whole catastrophic forgetting problem.
It is. And to manage that balancing act, they need a really sophisticated reward design. For the agent and reasoning tasks, it's a mix of an outcome reward, a penalty for being too long-winded, and a language consistency reward. For more general tasks, they use a generative rule model with structured rubrics. This whole complex system is how they manage the trade-offs between accuracy and just efficient generation.
Okay, let's get to the payoff. This entire massive engineering effort was, for one thing, efficiency. How much did the complexity actually change?
It's a fundamental shift.
Yeah.
DSA takes the core attention complexity from that quadratic O of L squared down to O of LK, where K is that small, fixed number of selected tokens. So it's essentially linear with respect to sequence length. That was the whole point.
Right, but let's be clear about the indexer. It still has an O of L squared complexity. Doesn't that just move the bottleneck instead of solving it, especially when L gets up to 128K?
That's a fair question, and it's a critical detail. While the complexity is technically O of L squared, the authors really stress that the amount of computation is orders of magnitude less than the full dense MLA in V3.1. Because the indexer has so few heads and runs in FP8, its O of L squared cost is more like a small, fixed tax you pay to enable the massive savings in the O of LK attention core.
And the benchmarks seem to back that up. The numbers they show on H800 GPUs, they show a pretty significant speed up for long context tasks, both for pre-filling and decoding, and the gap just gets bigger and bigger as you get closer to that 128K token mark. It really shows the efficiency at scale.
And we're also careful, for shorter sequences where DSA doesn't help as much, to implement a special masked MEK mode to make sure there wasn't any performance loss there.
So, the million-dollar question, did it hurt the model's actual capabilities?
That's what's so surprising. The headline finding is no, the introduction of DSA did not cause a major widespread drop in performance. A benchmark like MMLU Pro held steady at a very strong 85.0.
And they actually saw some gains in specific areas, didn't they?
They did. The Search Agent Browse Comp score went up. The Codeforces Divi1 rating saw a nice jump from 2046 to 2121, and there was a small bump on AME 2025.
But not everywhere. There were a few drops in some really tough reasoning benchmarks, like GPQA Diamond in Humanities Last Exam, which at first glance, that looks like the trade-off, right? You get efficiency, but you lose some of your peak reasoning power.
It does look like that, but the paper gives some really important context here. They argue that the lower scores on those specific tests were because V3.2 Excited Quai just naturally generates fewer reasoning tokens. It learned to be more concise.
So it's not that it couldn't reason, it just finished faster.
That's the argument. And they say that the performance gap all but disappears when you compare intermediate checkpoints that are forced to generate a similar number of tokens. So the drop might not be an inherent flaw in the sparse architecture itself, but more of a stylistic change that came out of that final mixed RL training, possibly from that length penalty in the reward function.
And what about training stability? Was this whole new system hard to control?
The training curves they show are almost perfectly aligned. For benchmarks like BrowseComp and SWE Verified, you can see the RL training curves for V3.1 and V3.2 XPIC tracking each other very closely, which is great visual proof that the DSA integration was stable even during that really intense final optimization phase. Hashtag outro.
So if we were to wrap this all up, the main conclusion seems to be that DeepSeek V3.2 XPIC really did manage to integrate this sparse attention mechanism successfully. It delivered huge efficiency gains for long context, shifting that core complexity from O of L squared to a much more manageable O of LK.
And it did all that while, for the most part, maintaining the incredibly high performance of its dense predecessor across math, coding, and reasoning. It's a pretty remarkable result.
It really feels like a practical, robust framework for actually deploying these ultra-long context models. You have this cheap, cost-effective indexer that acts as a guide for the much more efficient core attention mechanism. It's just a brilliant optimization strategy for the real world.
Right, the main achievement is a solid proof of concept for high-quality, long context sparsity, but the authors themselves point to the next critical step. They're pushing for more large-scale testing in real-world scenarios to see what might break. And that leads to the final thought I'd leave you with. Given that this whole system relies on a fine-grained selection of the top K tokens, what kind of subtle, long-range global dependencies might it miss? Think about those needle-in-a-haystack problems, where a single seemingly unimportant token from 100,000 tokens ago suddenly becomes critical. Will this kind of sparse attention always be able to catch that? That's the kind of limitation that today's benchmarks might not be able to find, but real-world use just might. And that's something we'll have to watch as these models get even better.